This is the Chapter 13 Correlation and Regression step-by-step tutorial. I will walk us through a full problem based on what we started working on in the Zoom session last Wednesday. The question involved a family furniture store and trying to basically assess the correlation between the firm's advertising expense and their sales revenue. Initially, theoretically, what we can point out is that what we expect of this relationship is that we're expecting a positive relationship. We're expecting that as the firm increases ad expense, so they spend more money on advertising, this will lead to increased sales revenue. This is just a very good guess, because if ad expense didn't increase sales revenue, why would anyone ever advertise? So first, let's start off by testing to see if there really is a relationship. So the first thing we need to find is the correlation coefficient, and the correlation coefficient is represented by R. Okay, and R can be found by the following process. R is the sum of x minus x bar times y minus y bar divided by n minus 2 times the standard deviation of x times the standard deviation of y. Before we can get to R, we need to find x bar, we need to find y bar, and we need to find the two standard deviations. So let's set that up. So I'm going to rewrite this chart. So x is, of course, our independent variable, and in this case the independent variable is our ad expense. I'm going to put it into ascending order, 1, 2, 3, 4. Y is, of course, our sales, so this is ads and this is sales, and once again I'm just going to match up each of those with their corresponding x variable. So this would be 3, 7, 8, and 10. Notice here when ad expenses were 1, sales revenue was 3, and that's just the way I've set it up. So remember, to find the mean, we just sum up column X and divide it by 4, and we get a mean of 2.5. And the mean of Y bar, or mean of Y, is same thing, add up the column, and we get 7. Now, to get the standard deviation, we need to find the squared deviations for each one, okay, and then add up that column. But before we do that, we're just going to also find just the pure deviations. And the reason we're doing that is because you can see here it's part of this equation. So x minus x bar, we'll create a column called y minus y bar. Okay, in order to capture all those values. So first one will be 1 minus 2.5, and we get negative 0.5, negative 1.5, 0.5, and 1.5. The deviations from y will be negative 4, 0, 1, and 3. All right, for our standard deviations, we need to square each of those, so we get x minus x bar squared. And then separately we'll create a column for y minus y bar squared. Okay, so we have negative 0.5 squared, we get 0.25, 2.25, 0.25, 2.25. The sum of this column is equal to 5. So to get the standard deviation of x, we get the square root of 5 divided by 4, which is n minus 1. And standard deviation of x is approximately 1.29. The standard deviation of y, we have 16 as the square of y minus y bar, 0, 1, and 9. For sy, the sum of this column was equal to 26 divided by the square by 4, and we get sy is approximately 2.94. Okay, so now we just need the product of the deviations. So x minus x bar, y minus y bar. So we would do negative 0.5 times negative 4, and we would get 6, 0, 0.5, and 4.5. Now the sum of x minus x bar times y minus y bar is equal to 11. So to get our correlation coefficient R, we would do 11 divided by n minus 1 times sx sy. So now let's find R. Let's fill in our values. So we get 11 over 3 times 1.29 times 2.94, and this gives us an R of 0.945. And so this is telling us this 9.945 is very, very close to positive 1. So this is telling us there's a strong positive correlation. Now let's test the correlation, or let's test the R, the correlation coefficient. So first thing we do, just like each time, we set up our null and alternate hypothesis. In this case, the proportion parameter is rho. That's the proportion parameter for R. And we'll say it's not equal to 0. So the alternate hypothesis is saying that the true population coefficient for correlation is not 0. And of course, the null would be that it's 0. It can be positive, or it can be decrease or increase as well. This, of course, is a two-tailed test. Step 2, we have to classify alpha, and in this case, let's use alpha of 0.05. Step 3, this is going to be a correlation t-test. Okay, step 4, we need our decision rule, and our decision rule, our t critical value, is based on alpha, degrees of freedom, and the number of tails. So our t critical value is based on an alpha of 0.05, 2 degrees of freedom, because degrees of freedom for correlation coefficient is n minus 2, and we have 2 tails. So let's draw our decision rule. When we look up our t-table, we find our t critical value is negative 4.303 to positive 4.303. All right, now let's get to our final step, which is the test. Step 5, and the t-test for the correlation is done this way. We have r times the square root of n minus 2 divided by 1 minus r squared. So t is going to be 0.965 times the square root of 2 over the square root of 1 minus 0.965 squared, which is equal to 5.355 or 5.36. Now if we compare this to our rejection region here, we find that we reject the null. Okay, and therefore what we have shown in this example is that there is a relationship between ad expense and sales revenue. Okay, now step 6 is our p-value. So the p-value for the slope, in this case, if we base it on the 2 degrees of freedom, it will be between 0.02 and 0.05. And we know that the p-value in that case will be smaller than alpha, therefore we reject the null. Since we established that there is a relationship between the two variables, we can now go on to look for the regression equation to see if we can use our relationship between these two in order to make predictions, such as if we spend X amount of dollars on ads, how much revenue would we expect? So here's the format of our regression equation. You see y equals a plus bx. I'm going to rewrite this equation in terms of our dependent and independent variable in the problem. So y is, of course, sales revenue, which is what we're trying to figure out and understand. A will be the intercept, y-intercept, which means that would be the amount of sales revenue when x is 0. So in this case, b would be the slope of our regression, and x would, of course, be at expense. So what we'll try to do is, using this equation, once we find it, and once we find the values for a and b, we can make predictions for sales revenue. So first, let's find the slope, or b. So to do this, we have r, which we found in the previous step, times sy over sx, which effectively is the ratio between the standard deviations. So our r was 0.965 times 2.94 over 1.29. This gives us a slope of 2.2. So what does that slope mean? Well, let's interpret it. This basically says for every additional dollar spent on ads, what would sales revenue be if ad expense was equal to $3.5? Okay, so what would we do here? We take y equals 1.5 plus 2.2 times 3.5, and that would give us a predicted value for y. This y hat represents the predicted value of y, which would be $7 in sales. So that is our prediction. All right, let's now go on to testing the slope. All right, so here's our test for the slope of the regression line. So step 1 is we have to identify our hypothesis. So we have H0 and H1. Okay, in this case, the population parameter for the slope is represented by beta, and we're just going to test to see if the slope is in fact different from 0, and which means the null is just that beta equals 0. This is a two-tailed test. Can we test if the slope is positive? Yeah, we'll just set this up. If we just wanted to know, test if the slope is positive, we would just say beta is greater than 0, which would mean the null would be beta is less than or equal to 0. So it would be the same way as we used in chapter 10 and 11. All right, step 2. Just like in our correlation test, we'll just use an alpha of 0.05. Step 3, this is going to be a t-test for the slope. Okay, step 4, our decision rule. Remember, it's our t-critical value. It's based on alpha, the degrees of freedom, and the number of tails. And just like in the correlation test, the degrees of freedom for regressions are n minus 2. Okay, so t-critical value would be the same as the previous one, which is 4.303, or plus or minus technically 4.303. So here's our rejection regions. So 4.303, negative 4.303 through positive 4.303. All right, now for the test, step 5. Okay, we do have to learn a few new formulas here. So first, the test statistic for the slope is found by doing b minus 0, and this 0, yes, is always 0, divided by the standard error of the slope, okay, SB. So let me show you how we get SB. So the equation for SB, which also can be found on your slides, and the equation for SB is the square root of 1 over n minus 2 times the standard deviation of y over standard deviation of x times the square root of 1 minus r squared. We can plug in all our values, and eventually we get an SB of 0.411. Now finally, to do our test and see if we reject or fail to reject the null. So our b, our slope, was 2.2 minus 0 divided by 0.411, and that's going to equal 5.36, which is actually just coincidentally very similar to the t-statistic for our correlation coefficient. That does not always occur, but in that case, we find that if we compare that to our rejection regions, just like before, we find that we will reject the null. Okay, so what does this tell us? It tells us that the slope of this regression is statistically significant, right, and different from 0. So there is a relationship between these two variables, the relationship is statistically significant and different from 0. Finally, let's find our p-value here, step 6. P-value in this case, once again, just like we saw previously, the p-value will be based on our 2 degrees of freedom and will be equal to somewhere between 0.02 and 0.05, which further supports our claim that we will be rejecting the null of this hypothesis. There's a few more variables that we need to look into, and one of them is called the r squared. The r squared is called the coefficient of determination. Okay, and the r squared, what it tells us is the percentage of the variation in our dependent variable that is explained by the variation in our independent variable. So it kind of gives us an idea of the strength of the explanatory power of our x variable in determining our y variable. So in our case, we had an r of 0.965. So if we square that r, we get a value of 0.9311. Okay, this can also be multiplied by 100 to yield us a value of 93.11%. So what does this tell us in terms of the question that we started with? It says that 93% of the variation in sales revenue can be explained by the variation in ad expenses. Okay, so what percentage can't be explained by ad expenses? Approximately 7% cannot be explained by the variation in ad expense, which means there may be other variables that might help explain that other component. But since we had such a strong R squared and such a strong relationships, that may or may not make sense to conduct multiple regression. All right, one other coefficient of interest is what we call the standard error of the slope, or the standard error between the two variables x and y. The standard error of the slope is found by the following equation. It's found by the sum of y minus y hat. Y hat is the predicted value for y. That gets squared divided by n minus 2. Okay, so let's set this up. Now, when we look at a scatter plot of this data, as we've done a few times already, okay, so something like this, and we ended up with our regression equation here. And our regression equation was y equals 1.5 plus 2.2x. Okay, so this is, of course, ad sales, and this was sales revenue. Okay, now the standard error of the slope helps explain the basically how well this line fit the data. And each, as I think we discussed this in a past video, but each of these points here, these black dots, those are actual observations. Those are actual y's. Okay, the predicted y's are these values here, just like we predicted in the previous step, where we said if ad expense was 3.5, we predict that sales revenue would be 7. So this was a predicted value of y. So this is y hat, or prediction. So remember, the goal of regression, or least squares regression, was to minimize this gap between actual values and their prediction. So this is here the sum of y minus y hat squared. This is called the sum of squared residuals. Okay, and we're going to calculate the standard error to understand how well this linear regression or equation fits our data. All right, so I'm going to rewrite our data here. We're going to have our x variable, our y variable, and I'm going to add y hat. Then I'm going to create a variable for y minus y hat squared for our calculation. I'm going to put the data in order. So we have 1, 2, 3, 4, 3, 7, 8, 10. Okay, and finding the predictions for each of these. If we plug 1 into our regression equation here, if we plug in 1, the y hat is 3.7, which notice is slightly different from the actual y that the data had already shown us. For an x of 2, the data results a predicted value for y of 5.9, 8.1, and 10.3. These are fairly close. You can see that probably the most divergent one looks like it's 3 and 3.7. So let's find those square or residual values between y and predicted y. Okay, so we have 0.49, 1.21, 0.01, and 0.09. Looks like the biggest gap here is in our when ad expense is $2 million or $2. We find the biggest gap there. Again, that could be purely coincidental based on monthly sales that we're looking at. So now finally, the sum of y minus y hat squared is equal to 1.8. So the standard error of our relationship, or of our entire regression, is going to be 1.8 divided by 2. We take the square root of that, and we get 0.948. Right? This is a very small standard error. And therefore, this tells us that the strength of the relationship is very strong, and that this equation does a really good job predicting our the relationship between the variables. All right, just to quickly show you guys just a little quick kind of idea capture in this correlation. So let's say we had this scatter plot, and we had one that looked like this. Okay, And if we drew in our line of best fit into both of these, you have one like that, and you have one that looks like that. Now, if we start to like compare to see how far each observation is from the y, you'll notice that really some of these line up. They're fairly, close. If we compare that to this, we'll call this panel A. If we compare that to the values from panel A, notice that's a big gap there. That's another large gap. It's another one. This is a very large gap, and so is that one's a little bit small. So if we were to predict a standard error for these two, the standard error for A is going to be much smaller than the standard error for B. The last step in our regression analysis is to generate confidence intervals and prediction intervals around our predicted y hat. So remember, we don't want to give exact predictions, okay? Because exact predictions may be wrong. So in order to give us, give your client, for example, that you're trying to forecast for, you want to give them a better idea, or more like a confidence interval of a possible set of numbers. So y is between y1 and y2, etc. Okay? So first let's start to look at the idea of the confidence interval, which is almost exactly the same as we did in chapter 9. So confidence interval, okay, so this tells us the mean value for a y, right, for a y, given some specific x that you're trying to use to predict a value of y. So the confidence interval is built to say this way: y hat, the predicted value of y, is plus or minus t, which is the t statistic that you can calculate from the t table, times the standard error of x and y, which is what we calculated in the previous step, times the square root of 1 over n, the number of observations, plus x minus x bar squared over the sum of x minus x bar squared. This x here that you subtract the mean from and square, this is just whatever independent variable you're using. Say, if you wanted to find out what's the predicted amount of y if, let's say, you spend $3 million on advertising, that would be the x you would plug in. All right, so let's use an example where we want to predict what is the predicted y hat, right, if we spend $3 million on advertising. So first thing we have to do is actually find y hat using our regression equation. So y hat is equal to 1.5 plus 2.2 times 3, right? This is we're trying to see what is the amount of sales if ad expense is 3. So we find that y hat in this case is equal to 8.1. Now, instead of just saying, well, that's it, that's the average value, if anytime you spend $3 million on advertising, you expect on average sales revenue of 8.1 million. Now, let's see if we can create a confidence interval, because we know that this is highly unlikely to be perfectly correct. Okay, so let's put in our other values. So y hat is our 8.1 plus or minus the t statistic or the t critical value at 95% and 2 degrees of freedom. So here the degrees of freedom are 2. And we're going to create a 95% confidence interval. Based on your t table is 4.303, which is pretty much, again, coincidentally the same number as the rest of our tests. Our standard error was 0.948, which we found on the previous sheet. We multiply that by 1 over 4 plus 3 minus 2.5 squared. Again, that's the 3 there. And then the sum of x minus x bar squared we calculated like back on the very first section of this tutorial. So once we solve that, we get the confidence interval is 8.1 plus or minus 2.23. Okay, so again, here now we have an interval of possible values between, since we don't know the true population mean, since we have only a few number of observations, now we have a confidence interval. All right, the prediction interval is when we're trying to figure out the individual value of y. So again, in this case, let's say a given month, for example, let's say we want to know if you spend $3 million in July, what is the expected sales? So in this case, in the prediction interval, the likelihood of the actual sales revenue is going to be a little bit less precise than in our confidence interval, where we were just trying to estimate a mean value. So the equation changes slightly and it becomes y hat plus or minus t, that's the same, syx, our standard error, that's the same. And what we see as the change is here in this equation, we have a 1 added in that square root, but the rest is effectively the same. Oops. Minus x bar squared. All right, so let's plug in these values and get our prediction interval. So our y hat in this case was 8.1 plus or minus the t we've already calculated, our 0.948, our standard error, times the square root of 1 plus 1 over 4 plus 3 minus 2.5 squared over 5. And we get 8.1 plus or minus 4.651. And again, notice that the prediction interval is slightly bigger than our confidence interval because this is trying to estimate a very specific expected number of or expected sales revenue in, say, a given month or a given day, etc. So just to look at this graphically, okay, so if we had our regression line, let's say something like this, right, our confidence interval would be a band like close around that regression line, and then the prediction interval would be a little bit further out. So the green would be our prediction interval and the blue would be your confidence interval. And that's pretty much it. That is the full process of trying to calculate the regression results. The slides give you another separate example of how to do this based on given data. The last thing that we will be working on in this class is to read an Excel printout of a regression. Okay, and that would be a separate tutorial that you will have available in the next day or so.